I have been mentioning before a generalized Hough-transform without saying what Hough-transform is. I will talk about Hough more. And the original Hough-transform is really a staple of computer vision. So let's look at this. All right, so what will we see on this slide? A very detailed version with 3 points and then another one with a few more points. What are we trying to do? Basically, I'm illustrating here with the linear Hough-transform. This was a technique first published in 1959, by the way, by somebody who was, by Hough, who was trying to analyze the particle traces left in one of these gas chambers, so a physics application. He patented it a few years later, and it's a really important concept in computer vision. So what is the linear Hough-transform about? Assume that we have a few observations in space, here in a two-dimensional space, 1 dimension, 2 dimensions, and we are trying to see if there is a line that would fit those observations. All right, now if we have just one line in that space, that's not terribly interesting, because why would we? I mean, we would just do linear regression and be done with it. It does get a bit more interesting when we have observations that seem to come from one line, and there can be a little bit of noise, of course. And if simultaneously we have observations that seem to follow a different pattern. For example, here we would have 2 traces in a gas chamber. And the Hough-transform gracefully extends to this. And then this problem, by the way, is no means trivial to fit with linear regression. So you can think about, okay, let's first fit one line and then subtract it and then do the other. But how do you even fit the first line in the first place? Yeah, so with just minimizing sum of square deviations, this is not going to work. All right, so what does the Hough-transform do? The linear Hough-transform proposes the following. Let's consider here on the first out of 3 observations, and let's put all lines that go through that observation. And well, each of these lines corresponds to 1 point in parameter space. Now, normally we parameterize straight lines in terms of a slope and an offset, but in an image like this, if we consider this line, the vertical lines with a slope of infinity, so that's not a convenient parameterization here. We want something that is a bit more agnostic with respect to what orientation we're going to see in our data. And the parameterization proposed here is the one shown on the left, one in terms of how long is the normal vector pointing to, or how far away is the line from the origin. If we project the origin on the line, how far away is it? And then the angle of this line. And so if we now look closely, for example, this blue line here in this parameterization, well, it goes exactly through the origin, so it has a distance of 0 from the origin, and the angle here is, what is it, 60 degrees or so, or okay, I'm trying to make sense of the color coding here. So it is blue, and all right, so the parameterization they give is an angle of 150 degrees and a distance of approximately 0. So why 150 degrees? Can somebody help me here? Because I was thinking this would be either something like 70 degrees, or it would be 70 plus 180, it would be something like 250 degrees. I don't know why down here it says 150. Anyone has a solution? Nico, because it's the angle between the x-axis and the normal of the straight line. So the, oh yeah, right, thanks. It's not the angle to the line, but it's the angle to the normal, and that's 150. Thank you. Okay. Then I further messed up. Okay, good. I messed up my assignment of lines from top to bottom. So this would be 1, this would be 2, and this one would be 3. All right, good. So this blue line gave rise to this point. This yellow line in this parameterization gives rise to this point. The red line in this parameterization gives rise to that point, and so on. So if we take all these lines that go through the first observation all together, if we did take all angles, it would trace out this part of a sinusoid. For the second observation, we can play the same game, and we will find this curve. And for the third observation, we will find, well, the third curve here. All right. Now, all these lines that go through all these points, there is one of them that pretty much agrees, namely, all have this purple line going through them. And if we look where it's purple, so all of them meet here. And what we can now do is we can well, either look for such intersection points in such a space here, or we could compute a histogram. So we could tessellate this two-dimensional plane here, and then we would count. So how many lines go through this box? 0, 0. There's 1 in this box, there's 1 in that box, there's 1 in that box, but there are 3 lines in this box here. So this is going to be our maximum, and so we can build this histogram, or in this literature it's sometimes called an aggregator, and then look for maxima in this space. So that works for straight lines, but it also works for other parametrized curves. Here's a second example. This time we don't have 3 observations, but this time each of the white pixels is 1 observation. And again, we can take, if we just pick one of those observations, we can ask for all the curves that go through it, and this will correspond to one of these sinusoidal lines in the Hough space. Now, if we do the same thing for all of the foreground points in this image here, we get lots of sinusoids, and well, in this example where there's no noise, they all intersect here and here, or half of them intersect on the left, half of them intersect on the right, and these correspond to the two lines that we found. So let's do this maybe with more colors. So there are two typical parameterizations which are being used. One was this angle of the normal vector and then the length of the normal vector. And the other parameterization that is sometimes used is to have the distance to a point and then the angle relative to the horizontal axis. And now after the first image, I'm a little bit shy to figure this out in real time here, which parameterization we have. So there is one at an angle of, yeah, I could read this maybe as 45 degrees and the distance of 0, and in the other case minus 45 and the distance of plus 50. So I would claim that the parameterization used here is relative to a origin of the coordinate system in the bottom left corner. And I would claim that the parameterization used here would be again the distance or the length of the normal vector, and here I claim it's the angle relative to the horizontal axis. If that is true, then this would be the red one, and these observations would contribute to that maximum over there. But so, in this space, we find local maxima, and then these local maxima each translate to, in the linear Hough-transform, to one line, which we can then project back to the image, as shown here on the right-hand side. And this is an example from scikit image. All right. So this works if we have things that are parametrized, or that if we have forms that can be parametrized very simply. There is an alternative. Let's look now. Remember that this is image and that we're in a computer vision class, and we can do more than just say, all right, I have a foreground pixel here and I can find all lines that go through this foreground pixel. After all, we've learned about convolution, and we've seen that we can estimate gradients, and from those gradients I can estimate local orientations using, for example, a method called structure tensor. Now, if I directly estimate for each, let's say for each image patch here, if I directly estimate for each image patch what is its slope and what is its, and I know what is its offset relative to the origin, then I can directly cast votes in a differently parametrized space where, for example, all these red patches here, they will be a little bit noisy, but they will directly cast votes for one region of space, and patches located on the other line will cast votes in another part of space. So if we do more work in the image space, then we will not get this kind of diffuse mapping. So not each foreground patch will vote for a whole curve, but then each foreground patch will vote for just a single point in that space. And well, then we're left with the task of clustering or finding local maxima in this new space. And there are various definitions of what a generalized Hough-transform is. This is what I will call the generalized Hough-transform now, to directly use estimates for the parameters, which I obtain locally from my image, and to cast a single vote in such a parameter space. Now, for more complicated problems, we can not just estimate slope and distance from origin, but as we have seen here, we can cast more complex votes, like where is the center of the closest pedestrian. And this is a trick that we're going to use in the next section, namely this instance segmentation by the generalized Hough-transform. And before we go there, I will again ask you for any questions that you may have.